Hello and good evening, everyone. Welcome to the third session for Drug Delivery Principles and Engineering. I hope I'm audible. Can someone confirm?
Good evening, ma'am. Yes, ma'am, you're audible.
Okay, thank you. I'll now share my screen. Let me know if you guys can see my screen. Can everybody see my screen?
Yes,
Yes,
ma'am.
ma'am.
Okay. Okay, so we'll start the session. So this is the third TA session for Drug Delivery Principles and Engineering. And in the third week, these were the topics that were covered. Control release for reservoir systems and non-erodible systems, as well as erodible systems and hydrogels. And I have some questions from previous year assignments and few numerical problems that were there for both week 1 and week 2 assignment, the current assignment, that also we will discuss. So this is a previous year assignment question. First question is, what is not correct about reservoir systems with orifice type of implants? Two options are correct here. The options are, they can greatly increase circulation of the drug in the body. The device can be excreted in urine and sweat. Drug release generally follows first order kinetics. Example, Procardia XL tablets, and the drug finds its way out of the orifice. The drug can be released by swelling control mechanism. Out of this, which two options are correct?
Ma'am, option 2 and 3.
2 and 3. Okay.
2 and 3, ma'am.
Okay.
2 and 3, ma'am.
Okay. Anybody else has any other answer? Which two options are correct? Anybody else would like to answer? Okay, then let's look at the answer. So these two options are correct. The device can be excreted in urine and sweat, and the drug release generally follows first order kinetics. So option 2 and 3. Most of you are correct. Yeah, so it actually follows a zero order kinetics, that is constant release, and it is easy to control the kinetics by the device design parameters. Further, it's a non-erodible system, so it's kind of an implant that will stay at this site. So it can be both erodible and non-erodible based on how you can design it, but it cannot be simply excreted using urine and sweat. Yes, so these two options will be correct. Here is the second question. So the assertion here is when a controlled release formulation is placed in biological medium, it immediately releases some quantity of drug as a bolus. And the reason for this is this burst effect is attributed to the time history of the device, with older formulations allowing diffusion of some quantity of the drug to the surface. Now, are both these options true? Both are false? Or the assertion is false? Or the reason is false? What do you think the correct answer would be here?
Both are true.
Both are true.
Okay. Others?
Ma'am, both are true.
Okay. Anybody else would like to answer? Anyone else? Okay, the correct answer is both are true. So the reservoir systems usually have this lag and burst effects. Here the question was about the burst effect. So that usually happens if you store the device for a certain period of time after you have prepared it. And within this time, what happens, the drug is more saturated near the membrane. And as soon as it comes in contact with your water, aqueous medium, or any other tissue, there is a instant release of uh, high level drug followed by a steady state constant release. So that is called the burst effect. There is also a lag effect where the membrane is devoid of any drug. So if you use the device immediately after fabrication, it will take some time to diffuse to the membrane and then it will diffuse from there to the outside. So that is a lag effect. So there will be initial slow rate followed by a steady state constant release. Okay, so here the correct answer was both are true. Here is the next question. Avidin conjugated to polymeric biotin is a type of what kind of hydrogel? Physical hydrogel, complex conservate, chemical hydrogel, ionotropic hydrogel, photolinked hydrogel, or enzyme linked hydrogel?
Ma'am, physical hydrogen.
Physical hydrogel, okay.
Physical hydrogel.
Okay. Anyone else? Anybody else would like to answer? Okay, the correct answer is physical hydrogels. So physical hydrogels are hydrogels where the polymer networks are usually held together by the neutral and ionic bonds, and that leads to molecular entanglements and involves several forces like ionic hydrogen bonding and hydrophobic forces. So the avidin biotin is one example, and another is the concavalin A with the polymeric sugar. These are some biospecific recognitions. Here is the next question. Porosity in non-erodible matrix systems can be measured by which technique? You have to select two correct options here. First is AFM or atomic force microscopy. Second is DLS, dynamic light scattering. Third is osmometry, surface plasmon resonance, liquid leaching experiments, and electron microscopy, followed by image analysis. Which of these
3, 4.
3 and 4? Okay. Sorry?
5 and 6.
5 and 6. Okay.
Liquid leaching experiment and the last one.
Okay. Anybody else has any other answers? Which techniques can be used to measure porosity in non-erodible metric systems? Anyone else? Okay, so the correct answer here would be the last two options. So if you want to measure the porosity, it can be measured by density and volumetric measurements or liquid leaching experiments and image analysis, basically by taking the image through electron microscopy. So the last two options will be the correct answer. Okay, here is the next question. Which of the following two statements are false for bulk hydrogels? I'll give you some time to go through the options and let me know what you think the correct answer is.
Hello, ma'am. Are the questions repeated from yesterday's session? I think these questions are covered in yesterday's session.
So there are three different TA for this course, and we all kind of are solving previous year assignments and some other doubts that you want to discuss. So more or less, it might be same. I
Okay,
haven't
ma'am.
looked through what was taught last in the last session, but yeah.
Option 4 and 7.
4 and 7. Okay.
4 and 6.
4 and 6. Okay. You have to select two statements that are false. Anybody else has any other answer?
Option 4 and 7.
Okay. So let's look at the answer. Most of you are correct. It will be 4 and 7. They are soluble in water and soluble for suitable for all delivery routes. So if you look at the options here, you have to select false statements. So the first option was hydrogels are three-dimensional hydrophilic polymer networks capable of swelling. So this is the correct statement for hydrogels. Then we have predictable and known swelling rates, correct. They are insoluble due to physical and chemical crosslinks which provide the network structure and physical integrity. This is also true. And because of this, they are not soluble in water. But here it says they are soluble in water, so this option will be wrong. They have low burst effects, correct. They are used in contact lenses, again correct, but they are not suitable for all delivery routes. So yeah, these two options will be the correct option. And here are some general advantages and disadvantages. They have low burst effects, known or predictable swelling rates, and reformulation of vehicle not necessary for different drugs. And the disadvantages is it's generally short release periods and not suitable for all delivery routes. Okay, this is the next question. What is the heat capacity of a system? Which of these options is the correct answer?
First option.
Okay,
Option 3.
option 3. Okay,
Second option.
okay,
Option third.
okay. We have a lot of different options this time for answers. Anybody else would like to answer? Anyone else? Okay, so the correct answer is the third option. Heat required to increase temperature of system by 1 degree Celsius is the heat capacity of a system. Here is the next question. When the drug load rate is greater than its solubility, which of the following is true for drug release from scaffolds?
First option.
First option, okay. Anyone else?
First
Sorry,
option.
first option, okay. Anyone else would like to answer? Okay, so first option is the correct answer. The interface between the dissolved drug region and the dispersed drug region moves to the interior front. So if you have the dispersed drug here, it slowly starts dissolving from the outer, and then this interface moves to the interior as a front. Here's the next question. The type of hydrogels that polymerize after injecting into the body are called
Option 3.
in situ cross-linking hydrogel.
In situ cross-linking.
Yes, ma'am. Third
In
option.
situ cross-linking.
Option 3.
Okay. Yes, all of you are correct. It's in situ cross-linking hydrogel. So basically here the gel forms at the site after injection, and the trigger of polymerization could be either time, temperature, or pH. But the main disadvantages associated with this is it may diffuse through the body if it hasn't gelled properly, and there is no control of shape. Okay, so here is the numerical question that was there, I think, in the first or second assignment. So a drug has half-life of 30 minutes in its native form, and PEG is conjugated to the drug to improve its pharmacokinetics, and the modified drug is injected intravenously with an initial plasma concentration of 1 mg per ml. And after 12 hours, the concentration of the drug in serum is 0.5 mg per ml. Calculate the change in half-life of the drug after modification, assuming first order kinetics of elimination. What do you think the correct answer would be here? I think you guys already submitted this answer for this question. You might have already gotten the correct answer here. We'll just see how to get that answer. Was anybody able to solve till now? What is the change in half-life of the drug after modification, assuming its first order kinetics of elimination? I hope I'm still audible.
Yes, ma'am.
Okay.
Ma'am,
Yes.
actually, I have given the correct answer, but then the accepted range is different. So I got it wrong. I mean, I lost my point for that.
You did not get it in the given range?
Yes, ma'am. Actually, not for this question exactly, but in the same quiz, I have given 5.167 as the answer, but the range is like only 5. So I didn't know that I was supposed to round off the values.
Mm-hmm.
Probably they should have given the range between 5 to 6. Is
Uh,
there something that
you can
could be done for
raise
this?
a concern in the discussion forum or something. You
Okay.
can reply uh, on the NPTEL forum. You can raise this concern, and they will look into it. Just put this in there.
Okay. Okay. I've solved this question, right? Do I share the answer?
Yeah, yeah.
I've gotten 11.5 as the answer.
Okay. I'll discuss the answer in some time. Anybody else has solved? Okay. Let's look at the answer. Uh, it would be between 11.2 to 11.9, but I've gotten an answer of 12. So if you're getting something like this, so you can always raise a concern. So if you have an initial, here the initial concentration is 1 mg per ml. So C naught would be 1 mg per ml, and after 12 hours, T equals to 12 hours, the concentration, that is CT, would be 0.5 mg per ml. So the new half-life would be, first you find the constant, elimination constant, which is Ct by C naught equals to e to the power minus kT, and here you get k equals to 0.05, and for half-life, Ct equals to 0.5 C naught, and then T half equals to 12 hours. This will be the correct answer. Okay, so here's the next question. A polymer is made of the following composition: 10 moles of molecular weight of 40,000, 15 moles with molecular weight of 45,000, 5 moles with molecular weight of 50,000. The PDI, polydispersity index of the polymer, is? Option 1. There is no option 1. If your answer is 1, then okay. Here you have to calculate the polydispersity index, which is, first you have to calculate the MW and MN, and then you calculate the polydispersity index from there. let's look at the answer here. So we have 10 moles of molecular weight 40,000, 15 of 45,000, and 5 of 50,000. So first we have to calculate Mn, which is summation of Mi by summation of Ni, which is 10 moles into the molecular weight. Similarly, moles into molecular weight, and their all summation divided by the number of moles. This will give us a value, and then you calculate the average molecular weight, average molecular weight, which is Mi square, uh, Mi square by summation of Ni, or number of moles into molecular weight square. You add all those values and then multiply the number of moles with the molecular weight and divide that from the above value. Whatever you get, you put it in MW by Mn form and you get the polydispersity index, which in this case would be 1. Okay. Here is the next question. A drug A is injected into a patient. The rate of elimination of A is 25 gram per minute and its plasma concentration is 5 mg per ml. What is the rate of clearance of the drug from the body in liter per minute? Assume that the drug distributes in total body water.
Ma'am, 5 liter per minute.
Okay. Anybody else has any other answer? Can you please repeat?
5.167. It's just a more accurate value.
Okay.
Look, 5 is the answer.
Anybody else? Okay. Here is the answer. So you have rate of elimination R equals to 25 gram per minute, 25 g per minute, and plasma concentration is given 5 mg per ml. So the rate of clearance or RC would be rate of elimination by plasma concentration, which is 25 gram per minute by 5 mg per ml. So you can convert this, change the units. So this would be 5 into 10 power 3 mg per liter and 10 power minus 3 and 25 mg per minute. So you'll get RC of 5 liter per minute. But here, as you can see, the range was 4.8 to 5.2. So if you're giving 5.167, it should still count. And if you still have the concern, then you can raise it on the discussion forum. Okay, here we have the next question. Consider that a drug A is loaded into two separate reservoirs whose drug releasing areas are in the ratio of 2:1 and loading concentration of drugs are in the ratio 1:2. What is the ratio of drug released in the same amount of time for these two reservoirs? Assume that the reservoirs are flat and non-erodible, and the drug diffuses through a semi-permeable membrane in both the cases.
Answer is 1.
Okay,
1.
okay. So we have one answer so far. Anybody else? Anyone else has any other answer for this question? Okay, let's look at the answer. So for membrane reservoir, this is the equation that we have where the amount of drug release is dependent on these formulas. So MT is equals to ADK CST by L, where A is the surface area, D is the diffusion coefficient, K is the partition coefficient, C is the drug loaded, and T is time, and L is the thickness. So here M is directly proportional to area and drug loading concentration of the drug. So M1 by M2 would be A1C1 by A2C2, and A1 by A2, or the drug releasing areas are in the ratio of 2:1. So A1 by A2 would be 2 into 1, 2 by 1, and the loading concentration are in the ratio of 1:2. So C1 by C2 would be 1 into 2, 1 by 2. So this would give a value of 1. So the correct answer would be 1. Okay, so here we have another question. Consider a microsphere of diameter 1 micron. Calculate the number of such particles that would be present in a 1 milligram given the density of the material is 1.3 gram per ml.
First and third.
First and third, okay. Anybody else?
First and third.
Okay. We have two answers so far. First and third. Anybody else would like to answer? Okay, let's look at the answer. So here the particle diameter is given 1 micron, or if we convert it into the meter, 1 to 10 power minus 6 meter. The volume of one particle would be 4 by 3 pi r cube, which gives us a value of 0.5 into 10 power minus 18 meter cube. So the given mass here is 1 mg and the density is 1.3 gram per ml. And if you calculate the volume from there, we have mass by density, which gives us a value of 0.769 10 power minus 3 ml. Now, if you convert this into meter cube, it would be 0.769 into 10 power minus 9 meter cube. So the number of particles would be this total volume divided by volume of one particle, which would be 0.769 into 10 power minus 9 meter cube divided by 0.5233 into 10 power minus 18 meter cube. This would give us a value of 1.469 into 10 power 9 particles per ml. And that is the first option. The third option, which has a similar value. So the first and third options are the correct answers. Okay, this was all the question I had. Also, apart from this, I think there was one more question regarding the second order constant that many people had doubt before assignment submission. But I think you already know both the answers, but both the options you can put uh, in the form of a to the power x plus, there were two values actually, c2 and c3, both power 0.5, if I remember it correctly. So you can put, since both have similar power, you can simply put it as c2 plus c3 to the power 0.5, and whatever the c1 value was there. So this is how the second option would be also correct for the second order reaction. If anybody has any doubt or wants me to go through any question again, we can do that. Otherwise, we can close this session here. And this entire session was recorded, so it will be uploaded on YouTube. You can access from the link that will be shared with you. And the presentation that I shared here also will be, it will be shared with you.
Thank you, ma'am.
Anybody has any other doubt or questions?
Ma'am, can you repeat the last answer again?
Sure. The particles answer, this one.
Yes. Yes.
Okay. So here we have microsphere of diameter 1 micron. So there is one particle that is 1 micron in diameter, and if you calculate the volume of this one particle, it would be 4 by 3 pi r cube, since we are considering it as a spherical particle. So so the r would be this half of the diameter into 10 to the power minus 6 meter cube, and if you put into the formula, you'll get a value of 0.5 into 10 to the power minus 18 meter cube. That is the volume of one particle. Now it is asking, calculate the number of such particles that would be present in 1 milligram given the density of the material is 1.3 gram per ml. So mass is 1 mg, density is 1.3 gram per ml. If you want to calculate the volume, would be mass by density. So 1 mg divided by 1.3 into 10 to the power 3 mg per ml would be, I've converted this gram to mg, so now you'll get a value of 0.769 into 10 to the power minus 3 ml. Now if you convert this to meter cube, you'll get this value 0.769 into 10 to the power minus 9 meter cube per ml. Now we have to calculate how many particles are present in this 1 mg in this particular volume. And since the volume of one particle is this, so you just simply divide the volume of this total, the mass and density given volume of that many particles divided by volume of one particle. So you'll get a answer of 1.469 into 10 to the power 9 particles per ml, which can also be written in the form of 0.1469 into 10 to the power 9 particles, 10 to the power 10 particles per ml.
Thank you.
Okay. Anybody has any other doubt? Sorry, I forgot to share the screen. So this was the answer again. Anyone else has any other doubts? Okay, thank you for joining today. We'll close the session here. See you next week.